All right, so when we talk about solving something called a differential equation, what we're solving is an equation that involves derivatives of a function, and we can solve these given some extra conditions that'll determine the constants and therefore uniquely specify the solution. So we'll be able to take information given to us to evaluate more specifically the actual antiderivative of a function, or second antiderivative of a function. So in this example, we're asked to find f if f prime of x is equal to e to the x plus 20 times 1 plus x squared to the negative first power. And then we're also given this condition here, which is important, that says that f of 0 equals negative 2. And you'll see how we use that in a minute. So what we're going to do first is we're going to rewrite this so that we can see it a little bit simpler. All right, so f prime of x is equal to e to the x. And then we'll rewrite this as 20 over 1 plus x squared, and hopefully that rings a bell. You will recognize that another way to write this here would be to say that that's 20 times 1 over 1 plus x squared, which is one of those antiderivatives we're going to want to remember. Okay. Sorry, just working out the kinks here. So plus 20. All right. So when I take the antiderivative of this function, I'm going to recognize, first of all, that the derivative of e to the x is just e to the x. Plus, and then the antiderivative of this 20 over 1 plus x squared is just going to be 20 times inverse tangent of x, because that 1 over 1 plus x squared is the derivative of tangent. All right, so then the last thing that we've been in the habit of doing is putting plus c over here, because there could be a constant, right? And that's where this piece of information they gave us about f of 0 comes into play. Because if I know that f of 0, plugging in a 0 here, gives me negative 2, then I can use that information to solve for c. So I can say now that f of 0 is e to the 0 plus 20 times inverse tangent of 0 plus c, and that has to end up equaling negative 2. So I can just solve this part of the equation here and figure out what c has to equal. Okay, so we'll go piece by piece. E to the 0 is 1, anything to the 0 is 1, plus 20 times, well, inverse tangent of 0 means what angle would give me a tangent value of 0. In that case, that would be 0. There could be a number of values there, but 0 plus c equals negative 2. All right, so this ends up being 1 plus c equals negative 2, or c equals negative 3. So what that did for us is it allowed us to specifically state what c has to be. So in my final answer, I can state that f of x is e to the x plus 20 times inverse tangent of x minus 3. And I don't have to put plus c because I was given the information to figure out exactly what that c value would be. And so that's what we're going to be doing when we're solving these differential equations. We're going to be given some information to figure out exactly what that antiderivative would be. All right, so here's another example, and I'd encourage you to do this one on your own, because I think many of you probably could just take the information we just learned and do this one on your own. It's a simple polynomial function, and this time we're given the second derivative, and we're asked to find the first derivative, but they've given us two pieces of information, which is all necessary because in order to find those constants, we need some information about these original functions. So if you're going to do it on your own, pause the video, do it on your own, and then press play and you can pick up from here. But now we're going to go through the solution. So the first derivative, based on the second derivative, is going to have to be a cubic. And 3 times what gives me 12? Okay, so 4x cubed plus x, this is going to have to be a quadratic term. And 2 times what gives me 6? Minus 4 times x plus some constant, right? And I'm putting c1 because I know that I'm going to have to take 2 antiderivatives, so there will be another constant there. Now I can do the same thing to this and find f of x generally, which is going to be x to the 4th plus x cubed minus x squared, what times 2 gives me 4, plus c1 x plus c2. All right, so we could have another constant. Now we have two pieces of information that are useful. So what I can do is I can plug in 0, and I know that this whole thing is going to give me 4. All right, so f of 0 is equal to 0 to the 4th plus 0 to the 3rd minus 2 times 0 squared plus c1 times 0 plus c2, and that has to equal 4. And the nice thing about all these terms is 0 to any power times anything all goes to 0. So c2 is equal to 4. So I solved for the second constant. Now I can solve for the first constant because I also know that f of 1 is 1. So I'm going to plug in a 1 to this function, 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus, I still don't know what the first constant is. It's being multiplied by 1. However, I do know that the second constant is 4 now, and that all equals 1. So now I can solve each of these terms. This is just 1 plus 1 minus 2 plus the first constant plus 4 equals 1. All right, I can combine some things. Those are going to cancel themselves out. C1 is going to have to be negative 3. So when I state the actual original function, f of x, I can plug in the values of those constants. So it's going to be x to the 4th plus x to the 3rd minus 2x squared plus, well, I should say minus 3, because that first constant is negative 3, x plus 4. And that is the original f of x function. All right, so you can see why we could do this with 3 levels too, right? We could have multiple different differential equations here. And if we're given some initial conditions, then we can satisfy those and find the original equation exactly rather than having to generalize with a plus c or plus multiple constants, right? All right, the last thing we're going to do today is just a sketching activity. So you're given this graph right here, and you're asked to sketch its antiderivative f of x. So again, this is a good thing for you to do on your own. Pause the video and try to sketch this antiderivative. All right, so let's talk about the solution here. I'm going to sketch it in yellow. So a couple things to consider. The slope of this function, f of x, is the function we're seeing here, right? So the slope of big f of x is this function. So when we're seeing negative values in f of x, that means that big f of x has a negative slope over those values, right? So since little f of x is negative here, big f of x has to be decreasing at that time. Also, it's given that f of 0 is 2, so we can start our f of x function right there at 2. And now I know that it has to decrease until this point, and then it's going to start increasing. And that makes sense because that's a 0 on your derivative function, so that's where the slope of the original function would have to be 0. So maybe I'll make it go like this. Okay. Decreasing, and then it's going to start increasing. All right, and it's going to be increasing rapidly, but then it's going to stop increasing so much. It's still going to have a positive slope until here, though. All right, so I'm going to sketch this function increasing rapidly until here, and then it's still increasing until there. All right, because that's another 0 on our derivative function. Then my function's slope has to be negative, very, very negative, and then it stops getting as negative at this point. So sort of like here where we had an inflection point, we're going to have something like that here. Okay, so negative slope, really negative slope, and then it stops being as negative of a slope, but it is still a negative slope, and it continues like that with a negative slope for the rest of the existence of this function, big f of x. All right, so hopefully your picture looked something like that. It's just a good exercise to make sure that we're interpreting the information from the derivative functions correctly. And then I'm going to send you guys out an assignment that goes along with this.